All right. Good afternoon, everyone. Happy Friday. Welcome to another session of Zoom. Just we're ending the first week of summer session, so I would like to welcome all of you. And thank you for submitting your homework for chapter 1, 2, and chapter 3 is due tonight, okay? So hopefully, but most of you have already submitted. I have graded chapter 1 and chapter 2 homework and quizzes. I need to work on chapter 3, and then I'll be posting it on Blackboard, okay? So let's see. So far, we have gone over chapter 1, 2, 3, and 4. And I'm going to review chapter 4. Midterm exam will be on chapter 2, 3, and 4, okay? Chapter 5 is a tedious chapter also, okay? It's a lengthy chapter, and I'm going to just introduce you to chapter 5 today, and I've already posted the PowerPoint for chapter 5. Thank you, Matt, for letting me know in advance that, I said, let me just post the PowerPoint presentation. Sometimes I use my own notes. Sometimes we use the, PowerPoint presentation, and that sometimes I create my own PowerPoint. In another situation, because there are a lot of pictures, I have to use the, publisher's PowerPoint presentation, or the other professor that taught the course, they share their PowerPoint, and so we don't have to create the PowerPoint from scratch, because there will be a lot of pictures, and those pictures are not easy to really create, and it takes time. So I think it's a nice PowerPoint, and please review that. And I've already posted the PowerPoint for chapter 2 and 3. So the midterm exam 1 will be on chapter 2 and 3 and 4. So I just wanted to know whether we should have a Zoom session on Monday or not. I know most of you are in overseas. There's a time difference, about 11 hours or 12 hours time difference. When it's a daytime here is midnight, or say 12 noon here is about 11 o'clock at night there. So it's a little not convenient, but let's see. I'm going to post the PowerPoint, the exam, not the PowerPoint, exam on Sunday, okay, on Sunday midnight. And because by that time, I mean, it doesn't make any difference because you guys are already asleep, okay? So I just mentioned that I'm going to post it at 8 a.m. to 10 p.m. on Monday, okay? 8 a.m. to 10 p.m. You don't need really that many time. You should be able to finish it in 2 hours, okay? 2 hours. But because of the time difference, so I'm giving you that window of time to be able to finish your work, and then make sure that you post, you take pictures and convert it to PDF, like what you have done for the quizzes and homework. And then you submit that to my Google Drive, okay? The email address. One student is still sending me, or two, to my USD email address. Please send it to the one that says Morteza 92128 at gmail.com. Send it to that, so I'm looking at everyone's work or folder on the same page. I see that some of you are still, sending the information to my USD email address. If you are one of them, I know who that person is, but please try to send it to my Gmail account, okay? Gmail. All right, great. Is there any questions? Any question? All right, if not, I will continue with the review and lecture, and then before we leave today, you can ask any questions you have. So let me see how many people we have. We have about 22 students showed up so far, and there are some students that are not really attending the Zoom session at all. And those of you that you're gonna, watch the videos, make sure that you attend the Zoom session. I think that's a good idea to do that. Okay, all right. So if it's an emergency, I understand that, but I think it's required for you to attend the class or via Zoom. All right, let's do this. Okay, on the midterm exam, for sure you're gonna have problems that you need to sketch PV and TV diagrams, okay? PV and I saw that some of you submitted the homework for chapter 4, but you ignored the TV and PV diagram. You're gonna lose points if you don't show your work for the process, state 1, state 2, state 3, 4, and so on. You must show your work on PV and pressure volume diagram or temperature volume diagram. Okay, let me just unmute this. Okay, all right, so again, on the exam, I'm gonna be a little bit tougher on the gradings because I wanna make sure that you're doing your own work and make sure that you do your work in an organized way, on a clean way. Do not just give me the answer and say this is the answer. I want you to see the work step by step, okay? I hope you get that, okay? I'm just recording this and it's to confirm that I have stated that, okay, clearly, that I don't like to see only the answer, say this is the answer for A and B and C, okay, all right, so make sure you show your work clearly, you submit your work that is legible, is easy to read. Some of your homework was not really clear, and it was a black color or some kind of color that was not really readable. It was off the chart, okay? I could not really read your work. So make sure your handwriting is clear and you don't compress your work on a tiny area. So a little bit of stretching, okay? A little bit of stretch, so. And then you combine all those pages on PDF file, and then you share your folder, okay? So describe the phase change process for a pure substance with appropriate names for each state, okay? Fix the state for simple compressible systems. Again, the PVT relation, so pressure, volume, and temperature or volume relationships, okay? Substances, a pure substance is uniform and invariable in chemical composition. That's a pure substance. A pure substance can exist in more than one phase, but its chemical composition must be the same in each phase. Phase, what is phase? A quantity of matter that is homogeneous throughout, let me see if I can move this, throughout in both chemical composition and physical structure. Okay? Homogeneity in physical structure means that the matter is all solid or all liquid or all vapor or gas, okay? So homogeneity in physical structure means that the matter is all solid or all liquids or all vapor. And example, drinking water with ice cube can be regarded as a pure substance, okay? Pure substance, because it's the same, ice it's water, okay? All right, so. Drinking water with ice cube contain two phases of water, liquid and solid, but it's a pure substance. But in terms of phase, we have a solid phase and we have a liquid phase. But the water and the ice cube can be regarded as a pure substance, okay? There is no other chemical added, okay? For example, if you add, ink, for example, you add ink to the water, so then that's not a pure substance. Okay, drinking water with ice cubes contain two phases of water, which we have a liquid phase and solid phase. And properties of materials, we had a phase diagram when we discussed that we have in a binary systems, we have a liquidus line, we have a solidus line, and also we have a liquid region and we have a solid region. and as temperature increases, the solid will be converted to liquid as temperature decreases. For example, if you have a metal, for example, look at copper or zinc and aluminum and so on. Okay, all right. So a fuel-air mixture in the cylinder of an automobile engine can be regarded as a pure substance until ignition occurs. Okay, a fuel-air mixture. What's the phase? The air we breathe is a gas phase consisting of a mixture of different gases. Okay? All right, so that's what we have. Vinegar and olive oil salad dressing contains two different liquid phases. Okay? All right, so, and this is the isobar on TV diagram. We call this isobar, okay? It's a slope upward, and the positive slope, and this is a negative slope downward. And if you sketch the dome in here, the dome, you know that to the left side of the critical points, we have the compressed liquid, and to the right side, we have vapor, okay? And then the middle somewhere, we have a mixture, okay? Saturated mixture, and also this is a vapor, or it depends on the temperature. We have a superheated vapor, and we have a saturated vapor, okay? So, and these are the state 1, 2, 3, 4, 5, and the atmospheric pressure is keeping constant 1 atm, okay? And the temperature is increasing, correct? There we go. So we have isobar. So this is called isobar pressure line, okay? Isobar pressure line. Saturation temperature, when you go to a table, you gotta be careful because when it says, you know, you need to interpolate, you may need to use the saturation temperature for that. Temperature at which a phase change takes place at a given pressure, or I call it invariant temperature, okay? It changes, okay, invariant. Saturation temperature, and then we have an isobar, and this is the language of TV diagram, the dome here, and we have we label this as compressed liquid region and superheated vapor region, and these are the isobar, okay, at a constant pressure is constant P2, and the same P2 is greater than P1 because the P1 might be given to you, okay? All right, so P1 is constant. So this is the line, we call that, you know, the vapor region line, and this is the liquid line, okay, or liquidus line, and critical point. So this is a mixture here. You might see that on, you know, on the exam, you need to show your work on TV diagrams, okay? TV diagrams. And so we have the information provided, and then you go to the table, and then if they ask you based on given pressure and temperature, you need to determine the other intensive properties such as a specific internal, a specific energy, or a specific volume, and a specific internal energy, okay? All right, so like an example I went over last time. And with that example, when you have all this information provided, all the intensive properties are recorded from the table, and then the question might be to calculate the work for each, you know, state and heat transfer for each state, okay? All right, so that is the, you know, the vapor, and this is a fluid, liquid state. All right, so I try my best to give you the metric unit, but if you have the US system, the pressure in 1.01 bar is converted to PSI, pound per square inch, which is a 14.7. And you have the book in front of you. You can always go to the cover page, or the first page, I call it, and you should be able to see all the units, okay? All the units are here. So that's something that you have plenty of time, so you should be able to convert units if it's needed. Okay, all right, so. And isotherm if you look at the isotherm versus isobar, the line of the slope upward. For isotherm, the slope is tilted downward, okay, downward. It has a funny looking on this side than this side here. It seems like it has a two parallel line, and the dashed line is showing here, but you can show that with a solid line. But that's a temperature constant, and here we have a constant pressure, or we call it isobar. Anyway, so review this, make sure that you have a good understanding of a PV and TV diagram. Normally on PV diagram, you use the isotherm line, and then on TV diagrams, you use the isobar, okay, isobar. So you have two separate diagrams. Like example I went over yesterday, okay. And there we go. It's just the isotherm, constant temperature, saturation pressure, pressure at which phase change takes place at a given temperature, okay. All right, fixing the state of a closed system at equilibrium is described by the value of its thermodynamic properties. Okay? We are interested in the intensive system properties, temperature, pressure, specific volume, and specific internal energy. So those are considered to be intensive properties, okay, of thermodynamics. All right, so great. These are all measured, okay, measured values, and a specific internal energy is defined, okay, defined. All right, so make sure that when you are dealing with the ideal gas, do not mix the equation that we have, the first law of thermodynamics for ideal gas law versus non-ideal gas, okay, non-ideal like water, okay, or some other substances. Reference state for water, internal energy is 0. For saturated liquid, the triple point temperature, 0.01 degrees C, see the entry in table T-2, okay? Again, become familiar with all the table. I mean, if you have you could make a copy of all the tables to have it in front of you, or you can just flip through the book and look for the table T2 to T9, okay? T2. All right, so here we have a specific internal energy on isobar. What happens to the specific internal energy during the constant pressure phase change process? As the temperature increases, of course, on a compressible, container, the temperature, as the temperature increases, the internal energy increases as well. For example, here at 100, we have 418.94 kilojoules per kilogram. At the higher level at 300, the internal energy is 2,810.51. All right, at the saturated mixture at 0.4, and then you have to look that up or in the table, or you have to just, like example I went over yesterday, we have to find the mixture, okay, quality for the region, we call it the mixture region, okay? So, all right, great. At the end of this section, you should be able to define and calculate the quality of a saturated liquid vapor mixture. You all know how to use because it wasn't a homework, and you did a good job, and you did well on the homework. Please, work hard, make sure that your midterm exam is as clear as possible, so I don't want to spend many hours trying to find out what you're doing, okay? Show your work step by step. It's almost 40 students, 40 times maybe 5 pages, 8 pages. That will be like a couple of days I have to spend, and grading your exam. Okay, not convenient. Okay, I'm okay with that, but the eyes, your eyes go, because I'm not printing every single exam. I have to stare at the computer monitor, and that is putting a strain on my eyes. Okay, all right. So I've never thought that I'm going to be teaching online. This is in 35 years. This is amazing time. And when the people ask me, "Do you want to go online?" I said, "I have no other choice." So I had to just get a certificate on the Canvas and Blackboard, so to be able to learn about how to use this technology. But anyway, guys, it's going to be over in 2 weeks, okay? So we are okay. Let's go to here. Again, make sure you indicate where you got your information. Okay, if you got the information from table T2, T3, indicate on the exam that this is where you got the information. All right, so table T2 to T3 is properties of a saturated water, okay, two-phase region. T4 is superheated water vapor. And then table T5 is properties of compressed liquid water. T6 to T7, properties of saturated R134, okay? And that's it. Instead of having water, we have different substance, okay? R value, or R134, or R12, and so on. So table T8, properties of superheated R134 vapor. T2E and 8E are the same tables in English unit. So, all right, this is a little bit of headaches, okay? So far we have practiced the metric table, but these are the English units table, okay? So just spend some time flipping through those tables and pages and understand the language of both units. In the United States, we use the English units, or we call it U.S. system of unit, and it's not British unit. It's FPS unit, foot pound second, or U.S. customary units. Okay, so again, properties. Make sure that if you're going to the table, say table T-4, try to copy down all the properties, such as a specific volume and internal energy, enthalpy, and entropy. For time being, we don't, for chapter 2, 3 through 4, we don't need to worry about the entropy. S is an entropy, H is an enthalpy. I'm going to go over the enthalpy, okay? Enthalpy. So these three will be part of the midterm exam, but S is not for the second midterm exam. That's the second law of thermodynamics, okay? So when you have been given the information for superheated water vapor table and 10 megapascal 400, you can go to that table and copy down the specific, if you have VG, VF, and the UG, UF, HG, HF, and so on, okay? So this is the table, and you know how to copy down. So we have the 10 megapascal or 100 bar, and the temperature is 400 degrees C. So you have the, you go all the way to this area here, okay? So as the temperature changes, these intensive properties also changes, the values will change. Okay, so we have V, U, H, S, and the units are given here. All right, so then those are the value for a specific volume, a specific internal energy, a specific enthalpy and entropy. Okay. You can, okay. And linear interpolation, we have already discussed that, okay? Everybody should become familiar with that, and you got to show your work on the exam, say this is how you got the values using the interpolation. A specific volume of superheated water vapor at 10 bar and 250 degrees C is bounded by linear interpolation. So I went over this yesterday, okay? So you know that that's a linear line, and you have this point here, which is at 200 degrees C from the table, and you get the specific volume of that value, 0.2060. At 240, you have this value. So then, because you need to find the specific volume and other properties, intensive properties, at that temperature, since it's not located, it's not given on the table, so you got to use interpolation. Okay, that makes sense? Okay. So just look at the note that I went over last time, and then you have an example in the book also, okay? Let me tell you this. Please review the examples in the book. Those are the good example problem. Make sure you have a good understanding of each example problem. line by line read that. Okay, all right. So you have the textbook or ebook, either the actual hard copy or you have ebooks. So make sure you review the materials on the examples. Okay. But anyway, I went already over this, so I'm not gonna just take the class, time this time to go over it again. I've already discussed that. Okay, all right. So, and that is, saturated liquid, saturated vapor, and all that. Okay. If we are in this region, we have a mixture. Okay. All right. So, again, it's saying that if you are within the mixture region, a system consists of two-phase liquid vapor mixture of waters at 6 degrees Celsius, and if the quality is given at 40% or 0.4, determine the specific volume of the mixture located the state on the sketch on the TV diagram, which is this here, okay, this area here. Okay. So that's the beautiful formula for determining the specific volume using the mixture for the mixture region. So you have the 6 degrees Celsius and you look for VF and VG. So you can just determine the specific one. Okay, that's very simple. Okay, great. All right, so the same thing, they're asking you to find for the given temperature of 180, which is not really given on this table, so you have to use interpolation. Okay, so far so good. And that's properties of superheated water vapor table T-4. After a number of times using this table, it becomes really comfortable or easy to get information from these tables. Okay, so. And then this is approximation of liquid. What is the specific volume for R134? And temperature 0 degrees and P equals 5 bar. So this is a saturated liquid line. And then you have a constant pressure, and that's the constant temperature line. Where the intersection is, you have the B of the liquid, that's the iso. This is an isotherm. This is an isobar. This is if it's an isotherm, it's going to be the line goes down and then goes up, and this is the isobar. This is slope upward and it's slope downward. Okay, so become familiar with that. Again, here is trying to say that the specific volume is a function of temperature and pressure, and as an approximation, we say that it is equivalent to or approximately equal to the specific volume of the liquid region. And for the internal energy, enthalpy and entropy, the same. Okay, all right. So enthalpy, if it's a capital letter H, that's the total enthalpy. So internal energy plus the product of the pressure and volume occurs frequently, which is this beautiful formula. I think the first time I've seen this, I went over this was about 42 years ago. And I looked at this and I said, what is this here? Okay, and so for you guys, I think this is a lot easier because you have taken chemistry, physics, and so on. Because I did not take the chemistry and physics in this country, so that when I started my undergrad and graduate level, I went directly to thermodynamics, and I was overwhelmed, and I go, wow, this is too much. But anyway, and even pronouncing the name of enthalpy and entropy and internal energy, the specific volume, those were really a challenge. But for you guys, this is easier. And again, as soon as you see the lowercase h, that means that's a specific, okay? A specific, because U divided by M, it will become a specific, okay? So a specific enthalpy is an intensive property of the system, and its value is included in the properties table, okay? So remember, this is very important formula also, okay? Just pay attention to this. Okay, so a specific enthalpy, which is H equals specific internal energy plus the work, PV work. So you can use this formula to find the enthalpy, but for some situation you can use the table. The result of the table will be the same as using this formula, but we have to be careful. Okay, I'm going to go over an example problems for that. And if you keep the pressure constant and temperature constant, all right, saturated liquid, you heat that, and then you can saturated vapor. Okay, you're going to have a saturated vapor. Okay, and that's what we have in here. And then we have PV equals nRT. And do not worry about nR bar, because this is really a universal gas constant versus the gas constant. Okay, so because the universal gas constants is R over N, or this is R bar means universal gas constant, and if you multiply N times R bar, you get the gas constant. Okay, so I think we have already discussed that with using R instead of NR bar T. Okay, you'd see that in the textbook also. So ideal gases also obey the ideal gas equation of a state. Use ideal gas model used to describe the behavior of gases as if the molecules are approximated as point particles. The molecules do not attract or repel each other. Okay. All right. So, and this is the lowercase pressure, specific volume, and then R bar T. Okay, and PV equals RT. I think this is more like it. Okay, we're going to be using this formula here. Okay, great. And then it says that enthalpy is a function of temperature, and internal energy is a function of temperature plus PV, and PV equals RT. So that will be the formula for H as a function of temperature. Okay, so here they're trying to derive the formula for a specific heats for constant at constant pressure and constant volume. And you already have the formula, approximation formula, which is for monoatomic gases and diatomic gases. So CV equals 3/2 times R, and CP equals 5/2 times R for monoatomic gases. And then for diatomic gases, you have to look that up. Okay, so that's a formula, how to evaluate changes in the specific internal energy and the specific enthalpy. Okay, because the delta U is CV as a function of time, temperature dt. So if it's substance is water, then you have to look that up in a table. But change in internal energy for ideal gases, you can say mCV delta T. Okay, M is the mass, CV is specifically the constant volume times the delta T, which is a change in temperature for closed system. For open system, the enthalpy for ideal gases will be mCP delta T. But if it's a non-ideal gas, you gotta be careful, because you have to find the information from the table, okay? Whether you are in a state 1, a state 2, or state 3 of the process that is given. So you have to be careful on that, okay? So here we have delta U, which is CV delta T. If it's a capital letter U, then you have mCV. So delta U divided by M, and capital letter U divided by M is a specific internal energy delta U. So the M is not there, okay? See that the M is not there. But if you have a delta U, the capital letter, then you can write mCV delta T, okay? But here for a specific internal energy and enthalpy, that's the formula, okay? All right, great. And then table T9, T11, you can go and find the, gives you the specific internal energy and its enthalpy as a function of temperature for several ideal gases. Okay. All right, so that's what we have for this review for chapter Do not save. Okay, let me just get our screen sharing as it stopped. Okay. Wow, what is this? Okay. Oof. All right. Let me escape from here. All right. So let's go over maybe one example problem. Okay. So I'm going to go to here. I need to connect the dock camera. That's why I got to just stop. Okay. So is there, and then let me see if I can go here, and AV is on. Okay. All right. So all right. So beautiful. Okay. Say we have, this is the exam questions. Okay. So we have a, let me just go here first. So we have 5 kilograms of water, initially a saturated vapor at 100 kilopascal, are cooled to a saturated liquid while the pressure is maintained constant. Okay? So 5 kilograms of water, initially a saturated vapor at 100 kPa, kilopascal, are cooled, okay, cooled to a saturated liquid while, let me see if I can move this a little bit up so I can see it. So, all right, so, and then the pressure is maintained constant. Determine the work and heat, okay? Determine the work and heat transfer for the process in kilojoule. Show that the heat transfer equals the change in enthalpy of the water, okay? So we want to prove that the heat transfer is equal to the change in enthalpy, okay? And this is a little bit unique situation, okay? Unique situation. Remember on the homework or example problem I went over, I didn't really ask you to calculate the work or the heat transfer, but if the same problem is given, maybe the question is to find the work and heat transfer. So let's look at the solution to that. So we have a PV diagram, and we have only one state. It says maintain a constant pressure. Okay, so let me just make it as, all right, so straight. On a PV diagram, so we don't have a TV diagram. This on PV diagram, we have a constant pressure, and we have a state 1 and a state 2. State 1 is the same as the vapor region, and state 2 is a liquid. So if you can see that the specific volume is the total volume over mass, or the total volume equals mass times the specific volume, okay? So we have the pressure and we have the mass. So the work is going to be the integrals of total volume from state 1 to 2 PdV, and that's equal to PV2 minus V1. Those are the total volume, okay? So if we want to convert that to a specific volume, we got to just substitute for total volume MV. So then we have MV or MP times the difference between the specific volume, okay? So if you go to table T-3, for 1 bar, you should be able to copy down the as state 2, which is the liquid phase, liquid region. You have this value, and then the internal energy you can copy down, which is at the this is state 1 is a vapor, and state 2 is liquid, and this is where we are at. Okay, so state 1 is a vapor, state 1 is a vapor, state 2 is liquid. All right, so you can copy down those information, the intensive properties. Then you're going to substitute the information we got from the table into this formula, and you have the pressure is 100 kilopascal, and then the mass is 5 kilogram. So 1 kilopascal is 1,000 Newton per meter square. Okay, so kilopascal is equals to one kilopascal equals to 1,000 Pascal. So a little bit of unit conversion, okay? Not the unit conversion because you have K means 1,000, okay? So Pascal means Newton per meter square. So because we don't say kilonewton per meter square, we say just Newton per meter square, okay? But we have Pascal, which is equals to one Pascal equals to 1 Newton per meter square, but 1 kilopascal is equals to 1,000 Newton per meter square. And then you substitute the specific volume, which is V2 minus V1, and V2 is the liquid. Remember that this is 10 to the negative 3. And then the VG is going to be V1, which is 1.694. And then you just come up with the work, which is minus 846.5 kilojoule. And then the first law of thermodynamics, if you wanted to solve for Q, is equals to change in internal energy and plus the work. And then the capital letter U, delta U, if you wanted to convert to delta U, which is a specific internal energy, we have to multiply by M, okay? M. Because M is equals to total internal energy the delta U, which is the change in internal energy as a specific internal energy, which is equal to delta U, capital letter, over M. So if you cross multiply, you get this here, right? So Q equals M U2 minus U1 plus work, so 5 kilogram. And then we already copied down the change in internal energy, a specific internal energy. So we have U2 minus U1, and then plus Q. Q is negative, so we substitute Q as negative value, because its heat is, when the heat is leaving the system, is going to be negative, okay, out of the system. Positive means going into the system. So you end up with a Q of the total, or the heat transfer. The heat transfer is minus 11,290 kilojoule. Now since we have this was calculated based on this formula, the first law of thermodynamics, and the question is whether the Q can be calculated using the enthalpy, okay, using the enthalpy instead of using this here, okay? All right, that makes sense. Let me just come back here so you can see that, all right? So we know that this part here, M U2 minus U1, MPV2 minus V1, we're gonna factor out the M, the mass is factored out, so we have U2 plus P2, okay, P2 V2, okay, if this is the P2 V2 minus U1 P1 V1, okay, at the state 1 and the state 2. So if we, because we know that from the definition that H is equals to U plus PV. So H1 equals U1 plus P1 V1, and so on, okay? So we have H2 equals U2 plus P2 V2. So U2 plus P2 V2 is H2, and M is factored out, okay? So minus H1. So if you substitute the value for internal energy, all right, so if you, if you substitute the value of the enthalpy from the T table, okay, so go to the same table, T-3, and look for this value, 17.46, at the same temperature or at the same, for the same pressure, okay, same pressure. And also, yeah, we have only pressure and mass, okay. So if you go to that table that we got this information here, you should be able to copy down this enthalpy. So if you multiply that, add and subtract and multiply by 5, this Q, the heat transfer, that we have in here is minus 11,290 is the same thing as what we have in here. This is a special case, okay? It's not valid all the time. This is only valid for constant pressure on a closed system, okay? So this is not true all the time. So there we go. So this is a type of problem you will see on now. And the materials that we have covered on chapter 2, 3, and 4, and make sure you review all that. And chapter 5, okay? Chapter 5, let me just go here. And if I wanted to share a screen for chapter 5. All right, so can you see this, guys? Can you see the slide for chapter 5?
Yes.
Yeah, okay, thank you, thank you. Let me go here. All right, so this is also chapter 5 is going to be a fascinating chapters. When I say fascinating chapters, because it's going to give you overall picture of thermal sciences or thermodynamics devices. When I say thermodynamic devices, we're talking about turbines, compressor, pump, recuperators, heat exchangers, and many other devices that we call it parallel flow heat exchangers, counter flow heat exchangers. It's under the umbrella of thermodynamic devices. Thermodynamics devices are very, very important in a design of gas turbine. You got to have a knowledge of maybe 2 semesters of thermodynamics and fluid mechanics to be able to understand the language of designing gas turbine, okay? An open system, closed system, and we have compressor, we have pump, and heat exchangers, and so on, and we're gonna be dealing with, okay, nozzles, and we have a nozzles and so on, okay? All right, so just one second. Okay, all right, so sorry about that. There was a little bit of distraction. Okay. All right. So if this will not be on the midterm, first midterm. Okay. So I've already posted this. You need to review this, my friend, for Tuesday's lecture. Okay. Tuesday, because Monday I leave it for you to work on the midterm exam. Because some of you have other classes also, or some of you are not really in the state. So I'm going to leave it up to you to review this before we have a meetings on Tuesday next week. So there will we're going to be discussing the mass rate balance and the rate of change of mass contained within the control volume at time t. And then we're going to be discussing the control volume and the mass within the control volume and the rate of change, okay? We're going to be dealing with m dot. M dot is the rate of change per unit of time. So the rate of change of mass contained within the control volume at time t it's a dm differential of the mass CV at the specific heat at constant volume over dt equals the m dot I. So the mass rate that goes into the control volume, into the system within the control volume, and minus the exit, okay, flow rate. So time rate of flow of mass in across the inlet I, inlet at times t, minus the time rate of flow of mass out across the exit E at time t. So this is the language that we will be communicating in terms of control volumes. Okay, this dashed line, we call it control volume. So the mass is inside the control volume. That's will be the topic of discussion. Okay, and we have a flow. Again, we have a mixture of fluid flow and thermodynamics, because in thermodynamics we have to design the device called pump or compressor or turbine. So if we have a pump, we wanted to design a pump so that it has enough power to, or with the, we have to calculate the efficiency of that pump and so on, so that it will take the matters or fluid or gas or oil or any other substance, can take it from one location to another location. Okay, so Here it says flow, a one-dimensional flow, and this is the velocity profile inside the pipe, the velocity profile, assuming the profile is uniform. Okay, we have an average velocity in the middle here. Flow is normal to the boundary at locations where mass enters or exits the control volume. All intensive properties are uniform with position over each inlet or exit area. A is the area. So you will be provided with the inlet velocity, inlet temperature, inlet in specific volume, and the area is pi r squared for the circular pipe, okay, or round pipe, or pi d squared over 4. So it will be a little bit of work. And then we're going to be talking about the steady state mass rate balance, and all properties are constant in time. And for a steady state, all properties are constant in time. For a control volume at a steady state, then this will be 0. Then we say sum of the mass flow rate inlet is equal to sum of the mass flow rate outlet. Okay, so this is the inlet and outlet if the left-hand side of this equation is 0. All right, so this is here, which is that is 0. Then sum of the mass flow rate of the inlet is equal to sum of the mass flow rate of exit. Okay, I think I'm going to stop here, and I would like you to, after the exam, just make sure you review this PowerPoint, and I'm going to go over a bunch of example problems and talk about the compressor, pump, turbine, heat exchangers, nozzles, and so on. Okay, all right. I think that's good for time being. Let me just have that here out of the way. Stop the share. Is there any questions, my friend? Okay.
How many questions are going to be on the midterm?
Honestly, I have not really designed the exam because I've been overwhelmed by the amount of work and trying to finish the Mesa College final exams grading. And then the grading for the mechanics of materials lab and all that. So it's not a good excuse, but honestly, I have not designed the exam yet. But I would say about 8 problems, 8 to 10 problems of 3 chapters, okay? Of 3 chapters. But you have plenty of time to do the test, so that it's not like you're in class and you have only 2 hours to finish the exam.
Professor, how much time do we have?
Okay, I'm going to post the exam at 8 o'clock, okay, on Monday morning. And then you need to work on the exam. And I mean, that's a Windows, okay? That's a Windows that is open from 8 to 10 p.m., 8 a.m. to 10 p.m. It shouldn't take you more than 2 or 3 hours to finish the exam, or say maximum, say 4 hours, okay? You can go to the moon and come back in 4 hours, okay? All right, so with the Mach number of 1 or 2 or whatever, okay? All right, so supersonic flow or speed, okay? I haven't designed the exam yet. I think it should be around 8 problems. Okay, any other questions? Okay, oops, my microphone was off, so now it's better. Okay, all right, so see how many people are here. Oh, okay, fantastic. 30 students are here. Jonathan, any questions?
No, it was just the how many problems, which you answered. Thank you.
Okay, you're welcome. Al-Ghanem, any questions, Al-Ghanem? Okay. Mai, any question?
No.
No,
Thank
okay.
you.
Oh, you're welcome. Mai, you submit your work. Did you submit your work to my USD email address? Yeah, I think so.
Yes, I think so.
Yeah, okay. Just please send it to the, like everybody else, to the Gmail, okay? Gmail account.
Okay.
Okay, thank you. Matt, any questions, Matt?
If we have any questions on the exam, will you be available during the regular Zoom time so we can ask them?
Yes, sure, sure. I will be available between 1 to say 2:30 and so on. So I will be available. Yeah.
Okay, thank you.
You're welcome. I think that's a good question. Very good, because if in case you have questions, you can just log in, because the account that you or the ID you have for the Zoom is recurring. It says for any time. You can just but since we have a Zoom session at 1 o'clock, I start at 1 o'clock. I will be available. Okay, I'll just wait for anyone to just ask questions during that period of time. Okay,
Thank you.
you're welcome. And let's see, and that's Matt, and then Michelle Almutari. No, any question, Michelle?
No, thank you.
You're welcome. Okay, take care. Mohammed, let's see. Okay, Mohammed Al-Twani. Okay, Mohammed. All right. Any question, Mohammed? No? All right. Abdullah Abu Zaid. Any Mohammed Abdullah Abu Zaid? Any question? No?
Okay, Professor, thank you.
Oh, no. Very good. Al-Sinan. Mohammed Al-Sinan.
No, thank you. I'm good.
Good, good. Very good. Mojtaba. Any question, Mojtaba? No? Okay. Mubarak let's see, Al-Amiri. Okay, Mubarak Al-Amiri.
No, I'm good.
Good, good. Very good. Monira Al-Turki. Any question, Monira? No? And Noah Marzuki. No, Marzuki. Omar, Renad, Salim, Samantha. Okay, I think that's those are the people that are attended the Zoom.